All right, let's dive straight into a fascinating paper today. It's tackling something pretty fundamental, a core bottleneck, really, in getting large language models to truly nail complex, multi-step tasks.
Yeah, exactly. We're talking about stuff that goes beyond just language understanding, things like multi-hop Q&A or math problems that need, a sequence of steps.
Right, where the model needs to reason, plan, maybe use tools. And this paper introduces a new method, stepwise reinforcement learning, or SWiRL. It's designed specifically to optimize for these kinds of multi-step challenges.
And the core idea is this two-stage approach. First, they generate a bunch of synthetic data showing these multi-step processes.
Okay.
And then stage two, they use a novel RL technique that gives feedback at each step along the way, not just at the end.
And the results they're reporting are pretty striking. Significant accuracy boosts, often double digits on tough benchmarks like GSM-8K, Hotpot QA, several others.
And maybe even more exciting is the generalization they found. Like, training on a question answering task actually made the model better at math. Completely zero shot.
Wow, okay. So training on Hotpot QA boosted GSM-8K by, almost 17%. That's huge.
It really is. It suggests something deeper is being learned.
So our mission for this deep dive is clear. Let's get under the hood of SWiRL, figure out how it works, why it's getting these results, and, why this could be a really big step forward for AI agents.
Good. Sounds good. Because while LLMs are amazing at text, that doesn't automatically mean they're good at breaking down problems, deciding when to use a tool, or pulling together info for multiple steps. It's a different skill set.
Okay, so let's start there. Why are these multi-step tasks so difficult for LLMs? What's the fundamental challenge?
Well, it's really the sequential decision-making. The model has to, first, decompose the problem, figure out the substeps.
Right.
Then it needs to realize, okay, I'm missing information here. Decide if a tool, like search or a calculator, can help. Then it has to formulate the right query or calculation.
And then process the result from the tool.
Exactly. Process the output, integrate that back into its reasoning, and then decide the next step, and finally pull everything together for the answer. It's like a whole chain of actions.
And I imagine if one link in that chain is weak or breaks, the whole thing can go off track pretty easily. That error can compound, right?
Precisely. Error propagation is a massive issue. A small mistake early on can lead to a completely wrong final answer, even if the later steps are sort of logical based on the wrong premise.
Okay, and how does this compare to, say, traditional RL approaches used for LLMs, like RLHF or RLAIF?
Well, those methods usually focus on the final output. They give a reward based on the quality of the entire generated response. They don't typically provide that fine-grained feedback on the intermediate reasoning steps.
Oh, I see. So they're judging the destination, but not really guiding the journey step by step.
You could put it that way, yeah. Which is fine for many tasks, but for these complex multi-stage problems, that step-by-step guidance seems pretty crucial.
Makes perfect sense. So SWiRL's two-stage approach aims to fix this. Let's break down stage one, the synthetic data generation. How do they create these examples?
Okay, so they start with an open source LLM, in this case, Gemma 2. They give it access to tools relevant to the task, so a search engine for QA, a calculator for math problems.
Right.
Then they prompt the model with a question, and here's the neat part. The model iteratively decides its next action. It can generate a thought, like planning its next move, or it can make a tool call, or if it thinks it's ready, generate the final answer.
So it's actively navigating the problem space step by step.
Exactly. If it calls a tool, say search, it generates the query. That query gets run, and the search results are fed back into the model's context for the next iteration.
Like it's having a little conversation with its tools.
Kind of, yeah. And this continues until the model outputs a final answer using some special markers.
Okay, so this generates what they call a trajectory, the whole sequence of steps. What's the structure there?
A trajectory is basically a sequence of states and actions. State 1 is the prompt, state 2 includes the prompt plus the first action and its result, and so on. The final action is the answer.
Gotcha.
And here's a key detail. They take a trajectory with, say, k steps, and they turn it into k separate subtrajectories.
Ah, okay. How does that work?
Each subtrajectory captures the entire history up to a specific action. So subtrajectory I includes the prompt, steps 1 to I1 with their results, and then focuses on predicting action I.
I see. So a single complex solution provides multiple training examples, each focused on making one correct decision within the sequence.
Clever.
Yeah, it lets them train the model on every decision point within those generated solutions.
And what kind of scale are we talking about for this synthetic data?
They generated a good amount, around 50,000 trajectories for Hotpot QA, starting from 10,000 questions. and about 37,500 for GSM-8K from 7,500 questions.
And they mentioned filtering out easy questions for Hotpot QA. Right, they wanted to focus on the ones that actually required multiple hops, multiple search queries, not just a single lookup. They also set max step limits 5 for Hotpot QA, 10 for GSM-8K.
Okay, but just having lots of data isn't enough. Quality matters. This brings us to the filtering strategies. How did they sift through this generated data?
Good point. They tried 4 main ways. First, the baseline.
Yeah.
No filtering at all. Use everything.
Okay, simple enough.
Second, process filtering. This is interesting. They used another powerful model, Gemini 1.5 Pro Thinking, as a judge.
A judge.
Yeah, to look at each individual step in a trajectory and decide if it was reasonable given the context up to that point. Crucially, this judge didn't see the final correct answer. It just evaluated the logic of the step itself.
Huh. Judging the thought process, not the outcome. I like that. What were the other filters?
Third was outcome filtering. Pretty straightforward. Only keep trajectories where the model's final answer matched the actual correct answer, the golden label.
Right, the more traditional way, maybe.
And fourth, the combination. Process and outcome filtering. So every step had to be judged reasonable, and the final answer had to be correct.
Okay, 4 strategies. What did they find? Which one worked best for training SWiRL?
This was one of the really surprising results. Across several QA datasets, Hotpot QA, Music, COP-CA, Beer QA, the process-only filtering consistently led to the best performance for the SWiRL model.
Just process filtering. Better than filtering for correct answers.
Yeah. Focusing just on whether each step seemed reasonable, regardless of the final outcome, yielded the highest accuracy gains. Figure 4 in the paper shows this pretty clearly.
That's really counterintuitive, isn't it? You'd think ensuring the final answer is right would be the most important thing.
You would think so. And what's more, outcome filtering alone often hurt performance compared to no filtering, except on one dataset, Music.
Wow. So SWiRL can actually learn effectively, even from examples where the model made logical steps, but still ended up with the wrong answer.
It seems so. It suggests the model benefits from seeing a diverse range of reasoning processes, even flawed ones, as long as the individual steps are plausible. This is quite different from supervised fine-tuning, where you typically really want clean, correct examples.
So process quality trumps outcome correctness for SWiRL training.
Fascinating. Okay, so that's the data. Now, stage 2, the stepwise reinforcement learning itself. How does this optimization work?
So they take the base model Gemma 2 again and fine-tune it using those subtrajectories generated and filtered in stage 1.
Right.
At each step within a subtrajectory, the model has to predict the next action or the final answer based on all the history, the prompt, previous steps, tool responses, everything.
So it's learning the optimal decision at every single point.
Precisely. And the guidance comes from a reward signal. They use another generative model, Gemini 1.5 Pro again, as a reward model.
Okay, and what does this reward model do? Its job is to evaluate the quality of the action the main model just took at that specific step, given the context. And again, importantly, this reward model does not use the golden labels. It's judging the inherent quality or reasonableness of the action.
So it's like the process filter, but now used to provide a reward signal during training.
Exactly. The objective then becomes maximizing the expected sum of these stepwise rewards over the whole trajectory.
And how do they optimize for that?
They use a policy gradient algorithm, similar actually to the RLHF methods used for Gemma 2 initially, but the key difference is applying it at this granular step-by-step level.
Got it. So this fine-grained feedback helps the model learn better local decisions, which adds up to better overall trajectory planning and execution.
That's the idea. Better technique throughout the game leads to a better final score, hopefully.
Okay, so that's the training. How does a SWiRL-trained model then tackle a new problem at inference time, when you actually use it?
It follows a very similar iterative process. Given a new question, the model decides, do I need a tool or can I answer now? If it needs search, it generates a query. That query is run, they mention, using Gecko Embeddings and a vector DB, and the results come back.
Okay.
If it needs calculation, it generates the math expression, which gets evaluated by a SIMPI interpreter, and the number comes back.
Right.
And this loop continues: decide, act, tool or answer, get result, until the model outputs the final answer or hits a max query limit, like 5 queries for QA, 10 for math.
So it's performing that learned stepwise reasoning interactively.
Now let's circle back to that generalization finding, the Hotpot QA training helping GSM-8K and vice versa. Can you elaborate on those numbers again?
Sure. training SWiRL on Hotpot QA, the QA task with search, gave a 16.9% relative boost on GSM-8K, the math task with calculator, in a zero-shot setting.
Impressive.
And training on GSM-8K gave a 9.2% relative boost on Hotpot QA. Table 2 shows this clearly.
And the significance of this is, it strongly suggests SWiRL isn't just learning task-specific tricks like how to format a search query. It seems to be improving the model's underlying ability to reason across multiple steps, plan, and use whatever tool is appropriate. It's a more general cognitive improvement, if you will.
That's really the holy grail, isn't it? General problem-solving ability.
Right.
Okay, they also compared SWiRL directly to standard supervised fine-tuning, SFT. What did that show?
Figure 5 lays this out. SWiRL consistently beat SFT on the QA benchmarks, regardless of the data filtering strategy used.
Oh, across the board.
Pretty much. Interestingly, though, SFT seemed to do its best when trained on data filtered for both process and outcome correctness, whereas SWiRL, as we discussed, did best with just process filtering.
Right. Why the difference, do they think?
Their hypothesis is that SFT has a tendency to just memorize input-output pairs from the training data. It learns to mimic the correct solutions it sees.
Which might not generalize well.
Exactly. SWiRL, on the other hand, because it's being rewarded for good steps rather than just correct final answers, is encouraged to learn a more robust, generalizable planning and reasoning strategy. It's learning how to solve the problem, not just memorizing solutions.
That makes a lot of sense. It's about the method, not just the result. What about the impact of allowing tool use during inference? Did that make a difference?
Yes, definitely. Figure 6 shows that using tools improves performance for both the base model and the SWiRL model. No surprise there.
Okay.
But the really crucial finding was that the SWiRL model showed significant gains even when tool access was turned off at inference time.
Oh, interesting. So even without the tools, it was better.
Yes. Which implies the SWiRL training itself improved the model's inherent ability to decompose problems and reason through them step by step, independent of actually calling an external tool. It learned to think better, essentially.
That's a powerful finding. It's not just about tool use proficiency. Did they look at how the amount of training data affected things, scaling the data set?
They did. Figure 7 shows the results for Hotpot QA training data size. As they increased the number of process filter trajectories from 100 up to 10,000, performance on Hotpot QA and the other QA benchmarks consistently improved.
A clear scaling trend.
Yes, and notably, they saw pretty significant gains even with just 1,000 trajectories. Suggests it might be reasonably data efficient, which is good news.
Definitely. And what about model size? Did SWiRL work better on bigger models?
The results in Figure 8 and Appendix B suggest it does. While the smaller 2 billion and 9 billion parameter GEMMA models benefited from SWiRL, especially in domain, the largest 27 billion parameter model showed much stronger and more consistent generalization to out-of-domain tasks.
So bigger models seem better able to leverage SWiRL to learn those general reasoning skills we talked about.
It appears that way, yes. The capacity of a larger model helps translate the stepwise training into broader capabilities.
Okay, nearly there. They also directly measured if SWiRL improved the quality of the intermediate steps themselves.
Right.
Using that reasonableness metric.
Correct. Table 3 shows this. SWiRL training significantly increased the average judged correctness or reasonableness of individual steps in the generated trajectories.
And this held true for both tasks it was trained on, like Hotpot QA, and tasks it wasn't trained on, like GSM-8K.
Yes, exactly. Both in distribution and out of distribution. It provides more direct evidence that the performance gains are coming from genuinely improved multi-step reasoning abilities.
Makes sense. And just quickly, they did evaluate the LLN judges themselves, the ones used for filtering and reward.
They did, yeah. Appendix C has details. For Hotpot QA, Gemma 227B as a judge had pretty low error rates. For GSM-8K, they compared Gemma 2, GMT 4.0, and Gemini 1.5 Pro.
And it found some differences.
Some nuances, like how harshly they penalized unit errors in math answers. Gemini 1.5 Pro seemed the most accurate overall for numerical tasks, so they used that primarily. But crucially, the relative results which models performed better stayed consistent regardless of the judge used.
Okay, so the main conclusions seem robust. And listeners can check out Appendix D for concrete examples of these trajectories.
Absolutely. They show both search and calculator examples step by step. Really helps visualize what the model is doing.
Great. So wrapping up, SWiRL seems like a genuinely significant step forward. It tackles that hard problem of multi-step reasoning and tool use in LLMs, and does it without needing tons of human labels or perfect examples.
Yeah, the big advantages are those strong performance gains, the really exciting generalization across different kinds of tasks, and this whole idea of using process-based feedback effectively. Rewarding good reasoning steps seems key.
It definitely unlocks a more robust way for these models to think, it feels like,
I think so too.
which really gets you thinking. What happens next? If we can reliably build AI agents that can handle complex multi-step problems, they can reason and use tools effectively, what kinds of new applications does that enable? Think about tackling really complex scientific research problems or building truly helpful assistants that can manage intricate multi-stage tasks for us. It feels like a major capability jump is on the horizon.
It certainly points in that direction. SWiRL provides a very promising path towards that more capable, autonomous AI.